As you saw from the previous video, sometimes it is necessary to apply integration by parts multiple times in one problem. We're going to see that on the next example as well. We have the integral of x squared times e to the 3x dx. In the situation where we have a power function times an exponential function, we have learned that it is convenient to let u be the power function. So we'll say u is x squared, then du is 2x dx. That leaves e to the 3x dx for dv, and when we integrate both sides, we're going to end up with e to the 3x over 3, or you can write that as 1/3 e to the 3x. So our problem, x squared e to the 3x dx, when we apply the integration by parts formula, becomes u, which is x squared, times v e to the 3x over 3 minus the integral of v, which is e to the 3x over 3, times du, which is 2x dx. So let's clean it up a little bit, and then we'll be able to see what we're dealing with. I'm going to write this as 1/3 x squared e to the 3x, and we can factor out constants here, call it 2/3 times the integral of x times e to the 3x dx. Remember, one of the goals of integration by parts is to yield an integral here that's simpler than the original integral. We have achieved that. However, notice on this new integral, we still have the case of a power function times an exponential function. So that is also going to require integration by parts. This second integral is of lesser degree than the original, but again, it does require another round of IBP. So let's try this again. Looking at this new integral, I'm going to let u represent the power function so that du is dx and dv will be the exponential part, e to the 3x dx. When we integrate both sides, again, we're going to get e to the 3x over 3. So applying this second round of integration by parts, we're going to copy down this original expression minus 2/3 times, now we're going to apply our integration by parts formula. Again, remember the IBP formula has two terms, therefore this set of brackets is necessary so that I can correctly distribute this constant to both of the terms that are coming. So within brackets we have u times v, u is x, v is e to the 3x over 3, minus the integral of voodoo, or v du. That's e to the 3x over 3. There's my v. And du is dx. Remember, with integration by parts, everything will be in terms of x. The u, the v, the dv, those are simply placeholders to help me get everything organized correctly in the formula. All right, let's see what we're dealing with here. We need to distribute the negative 2/3 to both terms here, and while we're at it, I'm going to factor a 1/3 in front of that integral sign. So we'll end up with 1/3 x squared e to the 3x minus 2/3 times 1/3 gives me 2/9 x e to the 3x. Now we're distributing a negative 2/3. Negative times negative is positive, and 2/3 times 1/3 is 2/9 integral of e to the 3x dx. We have finally arrived at an integral that we can evaluate directly. The integral of 3 to the x dx, again, something we can evaluate in one step. So let's go ahead and do that. Let me move my work up here. So continuing our problem, x squared e to the 3x dx, we have arrived at 1/3 x squared e to the 3x minus 2/9 x e to the 3x plus 2/9, and we're ready to integrate our exponential. So we're going to make a copy of the exponential and divide by the derivative of the exponent, and we are ready for the plus c. So simplifying the coefficient on that last term there. We have plus 2 over 27 e to the 3x plus c. Now that's a pretty good answer, but do notice that in the first three terms, we have a greatest common factor of e to the 3x. Also notice that we have fraction coefficients. So I want to factor out the GCF and attempt to clear up those fractions at the same time. So notice what I'm going to do. I'm going to factor out 1 over 27 e to the 3x. 27 is the common denominator between 3, 9, and 27. When I factor it out of the first term, I'm going to end up with 9x squared. Do you see how I came up with the 9? Notice 1 over 27 times 9 equals 1/3. So it's a form of getting a common denominator here. Working on our second term here, we have minus, remember we factored out e to the 3x. I'm going to think of what do I need to multiply that denominator 9 by to get 27? Well, that'd be 3, so I'm going to multiply the numerator by 3 as well. There's already a negative 2 up there, so my new numerator is going to be 6. Again, double check 1 over 27 times negative 6 over 1. If we factor out a common factor of 3, the resulting coefficient would be negative 2/9. So you can see that by factoring the 1/27th on the left, what's remaining inside here, and all I need is parentheses, is going to be a polynomial without fractions. The last term's pretty easy. It's just a cute little old plus 2, plus c. Now, this version of the answer is really the best version of the answer because I can really understand the nature of that function. I can see that it's the product of an exponential function times a polynomial function. Now, in this particular case, the power function that we were dealing with in the original integral was simply an x squared. And with each round of integration by parts, the degree of that power function decreased. As polynomials are differentiated successively, the power always decreases and eventually it differentiates away to 0. That's not true for your transcendental functions, right? But consider, what if instead of an x squared power function, I had x to the 5th or x to the 10th? That would take multiple rounds of integration by parts. So the purpose of this video is to teach you something called the tabular method, which is a shortcut to what we just did. Now, if I'd showed you the shortcut first, you wouldn't appreciate it unless you had been through the tedium of working that example. So we're going to rework this same example using a shortcut called the tabular method. So when we use the tabular method or a table method, we're going to contain a table of information. I'm going to have a column for a sign, which is going to alternate. I'm going to have a column for choosing the u substitution and a column for dv. We're going to start with the positive sign, and then we're going to alternate as we work down the table. So I'm going to begin with a plus sign. Now remember, the first choice of u in the problem we worked previously, we said u is the power function x squared, and we had dv to be e to the 3x. Now, on the next row of my table, I'm going to alternate sign from positive to negative, and I'm going to differentiate the u. The derivative of x squared is 2x. And then I'm just going to keep differentiating until I get down to 0, okay? And I'm going to keep alternating the sign until I get down to 0. So you can see that letting u be the power function and differentiating multiple times over, we eventually differentiate away to 0. Now, as I work on the dv term, instead of differentiating row by row, I'm going to integrate row by row. So on the next row, I'm going to integrate e to the 3x to get e to the 3x over 3. Then on the next row, I'm going to integrate again, e to the 3x over 3 times 3 or 9. And finally, e to the 3x over 9 times 3 or 27. So again, as I work down that integral table, I'm integrating each time. Now here's how the tabular method works. I'm going to multiply across here and then diagonally here. Okay, so I'm going to multiply here, diagonally here. Multiply across, diagonally here. And then we know we can stop here because the next one is 0. That's not going to lead me anywhere. So I'm going to stop with that previous term. So here's how we're going to put it together. The original problem was the integral of x squared e to the 3x dx. Again, we're going to multiply across row 1 and diagonally across column 3. So we're going to have positive x squared times e to the 3x over 3. So my first term is x squared times e to the 3x over 3. Working our way to the next row, we have a negative 2x times e to the 3x over 9. And finally, we have positive 2 times e to the 3x over 27. And then we'll tack our arbitrary constant there on the end. Now, is this looking familiar? It should. When we clean it up here, and then we can factor out our greatest common factor again, we're going to get exactly the same thing that we did on the previous example, but it was a little bit less work. Okay, so once again, I'm going to factor out e to the 3x over 27, or you can write it 1 over 27 e to the 3x. That's going to leave behind 9x squared minus 6x plus 2 plus c. So if we compare this to our previous answer, you can see they are identical. So the tabular method is a fast and efficient way to do multiple rounds of integration by parts in an efficient, very fast and efficient way. So use the tabular method when you have a power function that is degree 2 or higher, and the product of that power function and an exponential or a trig function. Hope you find that shortcut useful. I sure do.